Welcome to Electronic Devices and Circuits Lab. In this video, today we are going to learn how to obtain the VI characteristics of a transistor in common base configuration. So we have to obtain the input and output characteristics as we did in the case of common emitter configuration and common collector configuration. So let's begin this discussion. So first of all, this will be the circuit diagram. Okay, so this circuit diagram we have to implement onto the MultiSim, as well as you can also implement the same circuit onto the breadboard. So here you can see that we are taking a NPN transistor. Here we have the NPN transistor, and then this is our base terminal. Okay, so here you can observe that this is our base terminal, and because we have to obtain the characteristics in the common base mode, okay, common base configuration. So therefore, you can see this particular terminal of transistor base is common to both input loop as well as in the output loop. So here it is grounded, and then this is our emitter terminal. Okay, this terminal will be emitter terminal, and this terminal is our collector terminal. So first of all, we have to take all these components. We have to take the NPN transistor. You can also take the PNP transistor, no issues. So here I have taken NPN transistor for our analysis. So here you can see we have taken the NPN transistor. Then you have to take 1 kilo ohm resistor. Okay, that should be connected into the emitter based loop. Then we are having a power supply, variable power supply. And in between, we have to connect one emitter to measure the emitter current. Okay. We have to also measure what will be the base to emitter voltage drop. Okay, to measure this voltage drop between base to emitter terminal, we have to connect another voltmeter here. Okay, so here you can see in the output loop, again I have connected 1 kilo ohm resistance, and then we have to apply the this particular supply. Okay, this VCC supply with this polarity. We just note down this particular polarity. Okay, this is positive side and this is negative side. And in the input loop, you can see that this is our negative side and this will be our positive side. Because we are taking the NPN transistor, okay, this is our emitter terminal, this is NPN transistor, okay. So to make this PN junction forward bias, okay, this base terminal should be at the higher potential than the emitter terminal. Then only it will be made forward bias. Therefore, we have made this type of polarity, okay. And normally the output loop should be in the reverse bias mode. So because this is NPN transistor, so this N should be connected to the positive side. So it is connected to the positive side, and this P is connected to the negative side of the battery. So this way we have to make the circuit diagram. First, we have to make this circuit diagram. Here we have connected another emitter, and here we have connected another voltmeter. Okay, so either you can connect the voltmeter, and if you don't have voltmeter facility, you can also connect the CRO to measure this potential drop. Okay, but here we have to essentially connect the emitters to measure the currents. You remember that here the emitter current will be in the order of milliamperes. Okay, and accordingly the collector current will also be of the order of milliamperes. That we have to keep in mind. Now, after making this circuit onto the breadboard or MultiSim, okay, we have to obtain the input and output characteristics. So what will be the input and output characteristics? You must be aware, you must have seen in several books. It will look like something, this picture, okay. You can see this input characteristics, okay. So here we are having this base to emitter voltage drop. Actually, here it is written as emitter to base voltage drop, but normally if you see, if you write base to emitter to base voltage drop, then it will be a negative quantity. Okay, it will be a negative, because this P side will be at the higher potential than the N side, and therefore emitter to base voltage drop will be negative. Okay, so basically we are having base to emitter potential here. Okay, it will be in the positive value. Otherwise, if we are writing emitter to base, it should be a negative value. Okay, and then here we are writing the we are having the emitter current. And then this emitter current will be actually obtained for different values of collector to base voltage. So different set of values of collector to base voltage we have to use, and then we have to obtain this characteristics. As you can see, it is obtained for collector to base voltage equals to 0 volt. Okay, and here this is obtained for collector to base voltage greater than 1 volt. Okay, so this way we have to obtain this input characteristics, right? Then similarly, here you can see this is our output characteristics. So again, in the output characteristics, we have to actually vary this collector to base voltage. Okay. So while in the input characteristics, what we are doing, so we are actually keeping this value as a constant. Okay. We have to first fix this particular value of VCC. So it will be kept constant, and then we have to change this VEE supply. So once you will change this VEE supply, there will be a corresponding change in the emitter current as well as base to emitter voltage drop, and that we have to tabulate in our observation table. Similarly, when you are making an observation table for your output characteristics, that time we have to vary this voltage. Okay, we have to vary this voltage. And while varying this voltage, we have to keep this emitter current constant. Okay, this emitter current should be a constant. Here you can see this. These are the emitter currents. Okay, here you can see this IE equals to 0 milliamperes. It is I equals to 1 milliampere, 2 milliampere, and so on. So emitter current should be kept constant, and then we have to measure the IC, okay, collector current, okay, while varying the collector to base voltage. So this way, we have to actually obtain this particular characteristics. So here you can see these steps, okay. You can go through these steps. You can follow these steps to obtain the VI characteristics. Okay, I will be showing you onto MultiSim how to obtain the characteristics. There you can read out, you can go through it, and you can see this type of observation table we have to make. Okay, input characteristic for VCB equals to 0 volt, VCB equals to 2 volt, and so on. Okay, so this way you can obtain the VI characteristics. So I will be obtaining for different values, but essentially it is the similar type of observation table. Okay, so this type of observation table we have to actually obtain. One more important point that about the characteristics, if you see, you will see this characteristics in the Robert and Boylston book. If you see, this is the characteristics in the Robert and Boylston book. It is given in this way. So here we are having the base to emitter voltage. Okay, base to emitter voltage. You just I said that this base to emitter voltage, if you see in the circuit diagram, okay, it should be a positive value, base to emitter voltage. Okay, here you can see this in the circuit diagram. Because we are considering the NPN transistor, this base to emitter voltage should be a positive voltage drop. So that's why here you can see in this picture, which is given in the Robert and Boylston book, this base to emitter voltage is positive values. Okay, and then we are considering VCB equals to 1 volt, VCB equals to 10 volt, and 20 volts. So you can see in this picture, this graph is almost the same. Only little bit, a very small variation in the graph you will be observing if you are changing the value of collector to base voltage. So this type of graph we are going to actually observe. Okay, again here you can see this your output characteristics. Okay, this type of characteristics we are going to obtain when I equals to 0 milliamperes. This current will be very small. Okay, it is of the nanoampere range. Okay, and then for I equals to 1 milliampere, 2 milliamperes, 3 milliamperes, this graph will be essentially constant. Okay, here you can see this almost constant. Okay, there is no much variation in the graph. It is almost a horizontal line. And here you can see in this particular section, this is your saturation region. Here you can see, even if you make this collector to base voltage a little bit in the reverse direction, okay, there will be a this type of section we have to observe in the output characteristics. Okay, there will be a change in the current will fall down, and there will be a certain potential at which it will become 0, and then this current direction will change. Okay, and this type of curve we are going to obtain. So let's go to this MultiSim software. So I have already made this circuit. Here you can see this circuit. Okay, whatever circuit I have shown here, okay, the similar circuit I have made. The only difference is that what I have done is I have not connected any resistance in the collector loop. Here you can see that I have not connected any resistance in the collector loop. But if you are performing the experiment onto the breadboard, you may connect 1 kilo ohm. But the point is, if you understand the common base characteristics, what we know is in the common base configuration, normally input resistance is very low and the output resistance will be very high, because this output loop will be in the reverse bias condition, and therefore this resistance will be very high. And therefore, even if you don't connect the resistance, you will be able to conduct this experiment. Okay, so in both ways you can perform your experiment, that you have to remember. So now if you go through this circuit, okay, just you see this circuit here, we are having this VEE potential. Okay, this potential we have to vary, 1 kilo ohm resistance we have connected. This is our ammeter, which is measuring the current. Okay, this will be measuring the emitter current. Okay, and then this potentiometer, this voltmeter we have connected, which is measuring the base to emitter voltage drop. This is the polarity of your voltmeter. This is connected to the P side, your base side. Okay, this is connected to your emitter side. So this will be the potential drop across base to emitter. Similarly, here we have another emitter. Okay, this will be measuring the collector current, and here we are having the VCC supply. Okay, so this way you can first configure your circuit. I have taken this transistor 2N3904. You can take any transistor, okay? You can take BC547, any other transistor whichever is available in your laboratory, okay? So just to obtain the VI characteristics in input characteristics, okay, in the common base configuration, first of all, we have to make this VCB equals to 1 volt, okay? First, we have to make this VCB equals to 1 volt, and then we have to change this VEE accordingly, right? These are the different values of the VEE. Then we have to obtain this values. Okay, I have already done this experiment and then obtained this, filled up this all table. So I will be verifying few of the data, and then a similar procedure you have to perform to obtain the results. Okay, so first we have to make the VCB equals to 1 volt. So I will be obtaining this input characteristics for VCB equals to 1 volt. Okay, so this value will be constant. Okay, I have to keep it constant, and then I have to keep varying this particular voltage. So here you can see that what will be the next value we have to take. We have to take 0.3. Okay, so first value is 0. Obviously, if you apply 0 volt, everything will be 0. So I'll be just checking out this second input condition. Okay, 0.3. I'll be making it 0.3. So if you make it 0.3, okay, just make this voltage equals to 0.3 volt. And then if you execute this circuit, okay, if we execute this circuit, you can find out this current essentially very small. Okay, this emitter current is very small, 1.11 nanoampere. And this is quite obvious because this transistor will not be in the forward bias mode, and therefore the current will be very small. And here we are getting this potential across this base to emitter drop is 0.3 volt. Okay, it is 299.99 millivolts. So it is equal to 0.3 volts. So here I have noted down this value. Here you can see 0.3, it is 0.3. This current is almost equals to 0. Okay. Next, we can verify this data. If you make it 0.5, okay. If you make it 0.5, then we can observe this variations. Okay. If you make it 0.5, you can see there will be a little bit variation. Okay. So here you can see this current now coming into microamperes order. Okay. 1.628 microamperes. Now this voltage drop is becoming 0.498. Okay. So that value we have noted down it here. 0.498, and this current is actually we are writing in the milliamperes. So that milliamperes will be 0.0016. Okay. This is what our value is. Now, if you make this input voltage, let us say 2.5 volt. Okay. I'll be checking out this particular seventh number input condition. Okay. 2.5 volt. If you make it 2.5 volt, then again we can see what will be the result. So you just make it 2.5 volt. So if we make it 2.5, then if you execute this circuit, what is the result? Yeah, here we can see this current is 1.819 milliamperes. Okay, so here we have tabulated this result. This current is 1.819 milliamperes. Okay, and this is the corresponding base to emitter voltage drop, which is 0.681. So that value you can see here, it is 0.681 volt. Right. So this way you can just verify all this data, or you can just change the VE potential by this step size. Initially 0, 0 0.3, 0 0.51, 1.52, 2.53, 3.54, 4.5. Then after that, you can increase this with the step size of 1 volt, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So if you check, we can also verify this last data. Okay, this is when we are applying 12 volt. You can see what will be the output. Okay, so just you make it 12 volt. Okay, so if you make it 12 volt, then please note down this polarity of the battery. Okay, this is negative side and this should be positive side, right? So if you make it 12 volt, here you can see this current is 11.268 milliamperes. So here we have noted down this value 11.268, and this is the base to emitter voltage drop is 0.732. So that you can verify here, 0.732. So this way, first table, we can obtain corresponding to VCB equals to 1 volt. Now again, we have to do the similar procedure, okay, for VCB equals to 10 volts. So what we will do now, first we have to stop it, then we have to make it 10 volt. So first we'll make it 10 volt. And then again, we have to start from this particular value. Okay, we should be 0, 0 0.3, 0 0.5, and so on. Okay, so I will be just cross verifying few of the data. So let us say if we take this value, okay, if we make V equals to 4 volt, okay, now VCB equals to 10 volt. So if you make it 4 volt here, okay, if we make it 4 volt, then you can observe this result. Okay, what is this result? So here you can see this emitter current is 3.306. So now here you can see this value. This value is 3.306. Okay, and the corresponding base to emitter voltage drop is 0.694. Here you can see this is 0.694. So this way you have to actually obtain all these results. Okay, now you have to keep on varying this all values, and then you have to note down all these emitter currents. Similarly, again, you have to change the VCB equals to 20 volt, and then you have to again note down all these values, right? All this base to emitter drop and emitter current, and then you have to obtain this complete data for your transistor, right? So after obtaining, again, we have to plot this particular characteristics, VI characteristics, and for that, I have already explained number of times. What we have to do is we have to first you have to select this VBE, okay, and then you have to select this another IE, then again you have to select this VBE, then you have this IE, and then again you have to select this VBE, then this IE. Okay, and after that you can go to the insert tab, and here we have this plot. Okay, so here you can obtain this plot. Okay, this type of a plot you will be able to opt, right? So you may be able to obtain this type of plot. So try to obtain this plot, you will be able to get it. Okay, maybe there may be a little bit error somewhere, but you will be getting this plot. Fine. So I have already plotted this picture here. Okay, you can see, I think I missed this data. Okay, while selecting, that's why that result was coming a little bit wrongly. Okay, so you just select from the top side, then it will be coming correctly. Fine. So here you can see this type of plot you are going to get, and here you can see this. If you enlarge this graph, okay, here you can see a very little bit deviation in the graph. You can observe a very small deviation. Okay, that you can verify from this characteristics. Okay, which is given in the Robert and Boylston book. So here you can see a very little variations. Okay, so that variation you can observe in this particular input. Now we have to obtain the output characteristics. To obtain the output characteristics, again, you go back to the same circuit. Okay, we have this particular circuit, and we have to obtain the output characteristics. So how to obtain the characteristics, output characteristics? We have to vary this VCC supply. Okay, and this VCC supply will be same as the collector to base voltage drop. Okay, remember that. Okay, this is very important point, because we have not connected any resistance. If you connect any resistance, that time you have to connect one voltmeter across this two terminal, as it is shown in this particular circuit diagram. Okay, if you connect any resistance, obviously this potential and this potential drop will be different, and therefore we have to connect one voltmeter here to measure this base to collector to base voltage drop. Fine. But because I have not connected any resistance in this circuit, whatever we are applying here, that will be directly appearing across this collector to base terminal. So here you can see, and this will be your collector to base voltage. Okay, so that we have to obtain by varying this particular voltage. We have to measure the collector current. Okay, by keeping this emitter current as a constant. Fine. So here you can see this table, observation table corresponding to this. Okay, so here we have this observation table. So this is our collector to base voltage, and you remember, because if you see this characteristics normally. Okay, if you see any characteristics of common to base, means in the common base configuration, here you can see this. Actually, this is the corresponding to VCB equals to a negative voltage. Okay, here you see this is the collector to base voltage is positive, but here in this section we are having a very little bit negative voltage we have to apply. Okay, this is minus 0.1, so this may be up to minus 0.7 or minus 0.75. So what I have done is, you can see this observation table, I have started with minus 0.7. Okay, and if you keep it minus 0.7, then we will be able to obtain a similar curve. Okay, so here you can see that I have started with the minus 0.7, and first we have to set this I equals to 0 milliamperes. So obviously, if you wish to make it means 0 milliampere, then obviously there will be no current. Okay, IC will be equals to 0. So you have to accordingly select this voltage. Okay, you have to accordingly select this voltage, so that there will be no emitter current, right? There will be no emitter current. I will be just measuring, I will be showing you a few data. Okay, for this. Okay, I equals to 1 milliampere. Okay, in the laboratory you may be able to exactly set this values I equals to 1 milliamperes, but Sometimes it may be a little bit fluctuating current, so it may be 1.001 or a small fluctuation may be observed, right? So if you make this VCB equals to minus 0.7, first we have to make this VCB equals to minus 0.7. So if you're making minus 0.7, it means that you remember in the laboratory, we have to change the polarity, okay, of this particular supply. Here I have just, because it is MultiSim software, I can put here minus 0.7 and accordingly it will change the polarity. But onto the breadboard, you remember you have to reverse this polarity. And then you have to apply 0.7 volt. Fine. So we have to make it 0.7 volt, and then we have to set this IE current equals to 1 milliampere. To make it 1 milliampere, this V in supply should be 1.713. 1.713. So here you see this voltage, I am calling it as V in. So it should be 1.713. So if you make it 1.713, I am calling this voltage as V in. So if you execute this circuit, you can see this current, this is emitter current, okay, is almost 1.001 milliamperes. So this value we have to first set. Once we are able to obtain this input emitter current, then we have to measure the other current. So here you can see this collector current is now showing negative sign, okay? So it is negative sign, right? So the meaning is the current is not flowing like this, but the current is going like this, okay? Because this positive terminal is connected over here, right? So the current will be going like this. Fine. So this current is actually minus 1.163 milliamperes that we have noted down here, minus 1.163. Okay. Similarly, you can again observe this data. Okay. Let us say this VCB equals to 0 volt. Okay. So if you make it 0 volt, let me stop it. Make it 0 volt. If you make it 0 volt, okay, and if you execute the circuit, then you can observe this current. This emitter current is no more constant. And you must be aware that why it is happening, because of the base width modulation phenomena. Okay. So when we are changing this potential, okay, when we are changing this potential, there will be a penetration of the depletion layer. And because of that, there will be a phenomena which is called as base width modulation that will happen. And because of that, this emitter current is increasing, right? So what we have to do, we have to again bring back this current to 1 milliamperes, right? So here I have already noted down the V in value corresponding to this. So corresponding to this V in value, if you make it 1.666, then this current should be around 1 milliampere. So what we have to do, we have to again change this value first. So I will be making it 1.666. And after making this value this, then if you execute this circuit, you can observe this current. It is exactly 1 milliamperes. Okay. And now here you can note down the corresponding emitter collector current. Okay. This collector current is now 0.993 milliamperes. So that I have noted down here. You can see it is 0.9929. Okay. 0.9929 milliamperes. Similarly, you can observe this data. This is VCB equals to 10 volt. So if you make it 10 volt, so first I will be making it 10 volt. Okay. This is 10 volt now. So if you again execute the circuit, okay, you will find you have to first observe what is the condition of your emitter current. This emitter current is now 1.004 milliamperes. A little bit variation in the emitter current is again observed, right? So what we can do, again, we have to bring back this current. So a small change in the V in will be sufficient to obtain this, right? So 1.663 volt. Okay, so what I have to do, again, I have to change this value a little bit. I can make it 1.663 volt, and then you can observe this current. This current is 1.001 milliamperes. Okay, it is almost 1 milliamperes. And now this value you can note down. So this current is now 0.994 milliamperes. So here you can see this value is 0.9. Similarly, you have to make it 20 volt. Then again, you have to observe this value. Then after 20 volt, what we have to do? Again, we have to obtain the same reading for I equals to 2 milliamperes, right? We have to obtain the same reading for I equals to 2 milliamperes. For example, if you wish, you can verify this data. Okay, let me verify this data, minus 0.6. So at minus 0.6, I'll be verifying this data I equals to 2 milliampere, right? So let us say if you make it 0.6, okay, minus 0.6, let me make it minus 0.6, making it minus 0.6. So we have to make this I equals to 2 milliamperes. So this I equals to 2 milliamperes will be obtained when V in equals to 2.686. Okay, 2.68. So you have to make it this value equals to 2.686. Okay. Remember, I have just measured all these values and then I have already written those values in the Excel table so that it will not take too much time to adjust these values. Again, when you perform the same experiment in the laboratory, you have to do the fine tuning. Okay. So if you do the fine tuning, you will be able to adjust this currents. Okay. So here you can see this value is now 2 milliamperes and the corresponding collector current here you can see it is 1.874. So that we have noted down here. You can see this 1.874. Okay, this value you can see. Hopefully you must be able to see this is 1.874, right? So this way you can observe all these values. Fine. You just try to verify all these values. A little bit variation in the V in we have to perform every time because this current will not be constant. So suppose again if you make it 20 volt, suppose, right? If you make it 20 volt, right? Let me make it 20 volt. Then you will obtain, again you can see this current will not be 2 milliamperes, but because of the base width modulation, it will again change. It is 2.008 milliamperes. Now a little bit change in the ammeter current you can observe, right? So again to make it 2 milliamperes, this V in should be 2.678. Here you can see this data. Okay, 2.678. So just make it 2.678. Okay, although it is a very small value, but these values matters when we are obtaining the VI characteristics. Fine. So 2.678. So if you execute this again, you can see this value is 2 milliamperes. Fine. And corresponding current is 1.989. So here you can see this corresponding current is 1.989. So hopefully you must have understood how to obtain, okay, this table. So you please try to obtain this table, okay, for the different set of values of IE. Okay, and try to keep this IE current constant whenever you are changing the collector to base voltage. Because of the base width modulation, it will change. So we have to bring back again the same current because this graph has to be obtained for the constant emitter current. Okay, so after obtaining this, I have obtained this curve for I equals to up to 4 milliamperes. You can also take more readings. You can make it up to I equals to 5 milliamperes, 6 milliamperes, and so on. So after that, you have to plot this curve. Okay, to plot this curve again, what we have to do, you just select this data. Okay, this is collector to base voltage, and then you have to select these data, right? This is the IC current. Please don't select V in. Okay, we have to select only IC current. Okay, these are the collector to base voltages, and these are the different currents. Fine. So this different currents value you have to select. You have selected a wrong column. So you have to select this VCB, then you have to select this IC current. Okay, then you have to select this IC current. Then again you have to select this IC current. Okay, then again this IC current. Okay, and then this. Then you can go for the plotting. Okay, so once you will plot, you will be able to see the similar graph, right? Similar plot you can obtain. So here you can see this graph that we have obtained. Okay, here you can see this graph. Just little bit you enlarge it. So here you can see this graph. Okay, so we are obtaining a similar curve which is normally given in the books. Okay, normally given in the books. This is a constant current, right? And here we are getting the saturation region. Obviously, if you further increase this voltage, okay, obviously if you increase this voltage further, you will be also able to verify this curve. Okay, a similar increase in the current you will be observing. So hopefully you must have understood how to perform this experiment. So please you try to verify all this table, okay, for particular transistors, okay. And if you have any further doubt, you can ask me by dropping your message in the comment box. So thank you for watching this video. Please stay connected with the channel. Thank you.